All right, so basically we have learned that using stability simulation, you can simulate the loop gain, and the way we do it is we can insert a probe, 0 voltage DC, 0 volt DC voltage source as a probe to probe the loop gain, right? Using stability simulation, and we may still have some small question regarding how we can simulate the closed loop gain, ACL, and the closed loop output resistance. Okay, so we're gonna see how we can do this. Let's start by looking at closed loop gain, ACL. Intuitively, what do you think we can do if I want to simulate the closed loop gain, ACL? So first question is, how do we define ACL? Closed loop gain. It's gonna be the gain from here, the input of the entire system, all the way to the output. Is this right? Okay, so this is actually pretty straightforward. It's just like what we did in other software. I can do AC small signal simulation to simulate the gain from here to there. Is this right? Okay, and in the simulation, I'm gonna make it very easy because Cadence actually differentiates DC simulation and AC simulation. So what I do is I simply bring out the property of the input voltage source. And in stability simulation, DC operating simulation, we assigned 2 volts to the DC operating point for the input terminal, right? And now I'm gonna add 1 volt as AC signal magnitude, all right? And the reason I use 1 volt is simply because I'm lazy. If I use another value, actually 1 volt is not reasonable. 1 volt is too large for small signal, right? However, in Cadence, it does not matter because what Cadence do is it follows small signal analysis to figure out the gain from one point to another point. It doesn't matter if you specify 1 volt, 10 volt, or 1 millivolt, or 1 micron volt. Okay, it will scale the result based on the AC gain. Okay, so if I use 1 volt, the nice thing is whatever I read at the output, that represents the gain directly. I divide the output by input, and input is simply 1, so it does not affect the result, right? So it only makes my life easier. All right, so I'm gonna specify the AC magnitude as 1 volt, click OK, and save as check. And now go to analysis. I no longer need to run stability analysis. I don't have to plot those loop gain results phase margin. I'm gonna focus on AC analysis. Then I go to analysis, choose AC analysis. All right, very simple, right? And I'm gonna sweep the frequency from 1 Hertz to 1 gigahertz. And after that, click OK. All right, nothing special. Then run the simulation. Okay, after simulation is done, I go to result, direct plot, main form, and from the main form, I'm gonna plot the voltage. All right, if I want to figure out the gain in dB scale, then I'm gonna plot it as dB20 because we are talking about voltage, right? And now I have to, on the bottom, it reminds me I have to select the net on the schematic. So I'm gonna plot the output. This represents the gain from input to output, right? So I simply need to click the output. Then after that, we can see a nice curve. And this curve makes perfect sense because the curve starts from 0 dB. This is a voltage follower. At low frequency, it's a perfect voltage follower. The voltage gain from input all the way to output. The closed loop gain, the closed loop gain ACL equals to 1, and in dB scale, this is 0, right? Nothing special. And if you check out the bandwidth, you can actually see what is the bandwidth. 3 dB bandwidth, perhaps, if you read it out, it's about maybe 44 megahertz, right? And likewise, I can also plot the phase. So if I can find my window, okay. I can also plot the phase. All right, and again, I have to select the net on the schematic. So go to schematic, click the net, and now I have another curve which represents the phase. Again, if I right click, I can split the strip, split the trace. So on the top side, I have the magnitude starting from pretty much 0 dB, and on the bottom, I have the phase. Okay, so this is the closed loop gain. It's different from loop gain. Okay, always remember loop gain means the gain for this loop, right? Going through the loop. But the closed loop gain represents the gain from the input all the way to output. All right, do we have any question? Okay, no, great. So with that, we have answered the question, how do we simulate the closed loop gain? All right, next, how do we simulate the closed loop output resistance? All right, so tell me, what is the definition of closed loop output resistance? It means when we have this feedback loop, then I test the output resistance from here, look back into the entire system, and see what is the output resistance, right? And let's guess, if I use AC simulation, can I do this? I think so. What I do is I can actually place a AC voltage source here, right? And I can disable the AC information from the input side. Now I'm gonna test what's gonna be the impact if I have AC voltage at the output side, right? But the tricky part is I can't make a direct connection from here to there, because if I do this, then the DC voltage of this guy is gonna mess up with your operating point. Okay, so now we have several choices. You can either insert a real large capacitor to block the DC, or you can consider changing this into a current source, AC current source, and you measure the voltage, right? So the idea is pretty straightforward. You have a voltage source here, then measure the current, divide the voltage by current, that's gonna be the resistance. Does this make sense? In that way, you have to worry about the DC operating point, okay? Or you can place an AC current source here, measure the voltage, and now you use the voltage divided by the current, you get the resistance. Okay, does this make sense? Do we have any question? No. So if that is the case, no question, then I'm not gonna do this. All right. What I want to do is I'm gonna show another simulation method for the output resistance. So basically, there is a very convenient tool. Just like we have stability simulation, we can easily find out the loop gain. We have another simulation that can easily find out the resistance without worrying about the DC operating point. Okay, so what I do is go to analog design environment, go to analysis, choose. I have a spatial analysis, XF, very nice analysis tool. Okay. It's actually, if you want to find a way to intuitively understand it, I think XF is more like maybe the counterpart of stability simulation. Okay, it's not accurate, but somehow you can understand like that. All right. So the frequency range, sweep range, we're gonna do it starting from 1 Hz to 1 GHz, and I'm gonna use a probe to probe the resistance. Okay. So go back to the schematic. I'm going to add a probe. As I said, this is a counterpart. So instead of using voltage source for stability simulation, for XF, I'm going to use a current source. Okay, and this current source, I'm going to make sure the DC current is 0 amp. If I have 0 amp of current placed here, it's never going to mess up with my DC operating point, right? That's a nice property. Okay, so with that, I have done my modification to the circuit. And keep in mind, this guy has 0 amp of DC current. It never affects the operation of the true amplifier. Okay, it's only a probe. All right. So now set up my XF simulation. So in XF simulation, you can either use voltage or use probe. We're gonna choose probe, all right? And then I'm gonna click select. Then I'm gonna click this current source, select this current source, okay? It's I4, and then click OK. So after this, we pretty much have XF simulation set up properly, okay? I'm not gonna run AC simulation. I can even disable the DC simulation. Then I run a simulation and it tells me XF simulation is done, okay? It's nicely completed. Then go to the result window. I'm gonna add another sub window to plot the resistance, okay? And go to ADE, result, direct plot, main form. I can plot transimpedance, okay? This pretty much stands for the impedance seen by this probe, okay? I'm gonna plot the impedance in magnitude because I care about how many ohms do I have for this output port, right? And it tells me select current source on schematic. So I'm gonna select this current source, and after that, I get this nice plot of resistance, okay? And this plot also is reasonable. If we check out low frequency, the resistance is about 30 volts per amp, which means 30 ohm, okay? And if you do a hand calculation, you'll find out the value should be pretty close, all right? And this should be a good representation of the output resistance you are looking at. All right, do we have any question? No, great. So now we have learned several ways of simulation. DC simulation simulates the DC operating point, right? AC simulation, I think most of the circuit tools have this simulation. You simulate AC performance, and normally we are talking about small signal performance, right? And we have a special tool, STB, for loop gain simulation. We have XF if you want to figure out the resistance, impedance, or transimpedance. All right, so with this, I'm gonna stop the second part of EDA tutorial